What if the rockets we have been building for 60 years are completely wrong? What if the answer to reaching another star was never fuel, never engines, never explosions, but light? Not science fiction, not a dream, an actual plan being built right now. Let me give you a number: 4.37 light years. That is how far Alpha Centauri is, our closest neighboring star system. And it sounds manageable until you actually think about what that distance means. Light travels at about 300,000 kilometers every single second. It covers the distance from the Earth to the Moon in just over 1 second. And even at that speed, it takes light more than 4 years to reach Alpha Centauri. Now forget light. Think about us. Think about what we actually have. Our fastest spacecraft ever built is Voyager 1. We launched it in 1977. It is still going. Right now, as you watch this, Voyager 1 is the farthest human-made object in existence. And in all that time, in nearly 50 years of flying through space, it has only traveled about 0.002 light years. At Voyager speed, reaching Alpha Centauri would take roughly 75,000 years. Let that sink in. 75,000 years. So here is the question that haunted scientists for decades. How do you cross that distance in a human lifetime? How do you get there in not thousands of years, but decades? The answer they came up with sounds absolutely insane. Forget rockets. Forget fuel. Forget everything you think propulsion means. The idea is this. You build the smallest spacecraft ever made. Something about the size of a postage stamp, lighter than a paperclip, and then you push it with light. That is it. That is the concept. You aim the most powerful laser array ever built at this tiny craft, and you fire. The light pushes it, faster and faster, until it is moving at a significant fraction of the speed of light itself. And here is the part that will make your brain stop for a moment. This is not a thought experiment. This is not someone's sci-fi novel. There is a real project behind this, with real funding, real scientists, real engineers working on it. It is called Breakthrough Starshot. So how does light actually push something? Let me break it down simply. Light has momentum. That sounds strange, because light has no mass, but it carries energy. And when that energy hits a surface, it exerts a tiny push. Right now, sunlight is gently pushing on every satellite in orbit. It is a tiny force, almost nothing. But tiny forces matter when your spacecraft weighs almost nothing. This is where the sail comes in. Imagine a sail, not a boat sail. A sail made of an ultra-thin reflective material, a few meters wide, incredibly light, almost impossibly thin. When you shine a laser on it, the light bounces off and transfers its momentum to the sail, pushing the spacecraft forward. Now picture this, an array of lasers on the ground, probably in a high desert somewhere, above the clouds and atmosphere interference. Lasers combining into a single powerful beam with a total output of around 100 gigawatts. Aimed at this tiny sail in orbit, you fire. In a matter of minutes, the spacecraft goes from 0 to about 20% the speed of light. 20%. That is roughly 60,000 kilometers per second. Nothing we have ever built has come close to that. And then it is gone. No engine running, no fuel burning, just a tiny chip of a spacecraft. Silent, sailing through the void between stars. The spacecraft itself, what scientists call a star chip, would carry miniaturized cameras, sensors, and a communication system, all packed into something smaller than your hand. At 20% the speed of light, the journey to Alpha Centauri would take approximately 20 years. 20 years. Compare that with 75,000. Compare that with the entire recorded history of human civilization. Agriculture is only about 12,000 years old. We have been writing things down for about 5,000 years. And Voyager, with all of our rocket technology, would need 15 times the span of recorded human history to get there. But this spacecraft, this chip with a sail, could do it in 20 years. There are people alive today who could launch this mission and live to see it arrive. And when it arrives, it would photograph the Alpha Centauri system. It would scan for planets. It would look for signs of atmosphere, signs of something. And then it would beam that data back across 4.37 light years. That signal would take over 4 years to reach us, but it would arrive. For the first time in history, humanity would have eyes in another star system. But here is where it gets complicated, because this plan has problems. Big ones. The first one is power. 100 gigawatts is an enormous amount of energy. For comparison, a large nuclear power plant produces about 1 gigawatt. You would need the output of 100 nuclear plants, focused into a single laser beam, fired for a matter of minutes. That infrastructure does not exist yet. Building it would be one of the largest engineering projects in human history. The second problem is aim. You are firing a laser beam from Earth at a tiny sail no bigger than a few meters. As that sail gets farther away, your precision has to be extraordinary. The slightest drift in the beam and you miss entirely. You lose the spacecraft forever. It drifts off into the dark with no way to correct course. The third problem is space itself. Between here and Alpha Centauri there is dust, gas, microscopic particles. At 20% the speed of light, hitting even a speck of dust is like being hit by a bullet. The spacecraft would need to withstand thousands of those micro-impacts over 20 years of travel. Engineers are thinking about shielding, about angles, about materials that can absorb or deflect those hits. But no material has ever been tested at these speeds. And then there is this. Once it is launched, we cannot reach it. We cannot fix it. We cannot adjust it. It is gone. Whatever happens out there happens. It is completely on its own. Here is what makes this different from every other wild space idea you have heard about. This one has serious people behind it. Breakthrough Starshot was announced in 2016. It is part of the Breakthrough Initiatives, funded by physicist and investor Yuri Milner. Stephen Hawking was one of its founding voices before his passing. The project has backing from major scientific institutions and has attracted physicists, engineers, and researchers from universities around the world. They are not just talking. They are doing real research into laser arrays, light sail materials, miniaturized electronics, and trajectory calculations. The science behind each piece of this puzzle is real, documented, and published. No one is saying this is easy. No one is saying it will happen in 10 years. But the people working on it believe it can happen in our lifetime, in this century. That changes everything about how you think about this idea. Imagine the moment. Somewhere in the 2060s or 2070s, a signal arrives from Alpha Centauri, not a natural radio wave, not background noise from the universe, an actual transmission, photographs, data, the first direct images of another star system taken by something we built and sent there. Imagine what those images might show. A rocky planet in the habitable zone, an ocean glinting in the light of a different sun, or nothing, emptiness, a system of gas and rock with no sign of anything alive. Either answer changes humanity forever. If there is nothing, we know the weight of that silence. And if there is something, that is a moment no language has words for yet. And this mission, this laser, and this sail, and this chip, smaller than your hand, could be the thing that gets us there. We spent 60 years believing that getting to the stars would take rockets the size of skyscrapers, enormous tanks of fuel, massive engines breathing fire. But what if the answer was always simpler than that? What if the most powerful thing we could aim at the stars was light itself? Somewhere right now, scientists are running the math. Engineers are testing materials. The groundwork for something that sounds impossible is quietly being laid. We do not know if Breakthrough Starshot will work exactly as planned. We do not know what a craft that small can survive. We do not know what it will find. But for the first time in history, reaching another star is not just a dream. It is an engineering problem. And humans are very, very good at solving those. So here is the question I want you to sit with. If we launched this mission today, and 20 years from now it arrived at Alpha Centauri, and sent back a single photograph of a planet orbiting another star, would that photograph change the way you see your own life? Think about that.